Hello, welcome to my tutorial channel, and today I'm gonna show you how to do an ACI moment check for a rectangular concrete beam that is singly reinforced. That means there is only one layer of reinforcement at the bottom, and the shape is rectangular. That's the cross section, um, and with a uh, steel yield strength of you know or stress, uh, 60,000 psi, and concrete strength, compressive strength, 4,000 psi. So I've gone ahead and put in all these numbers here. This here is the modulus of its elasticity of steel, which is 29 10 to the power 6 psi. Um, and so the beam, the B is basically the width of the beam, which is 12 inches. The height, which is H, is 27, and this 24 value is called D. It's the distance between the reinforcement and the top layer, extreme fiber of the concrete. All right, so that D here is 24. Okay, so in this case, there is a, let's say, pretty simple step, really, especially that the beam is a simple shape, cross section, and um, one layer as well. That's not very complicated. So you'll use this. Usually, this step should work most of the time. I don't know. I don't know if it will work for every beam, but for this type of beam, this type of cross section, one reinforcement should work. So let's go ahead and check this. So here you have for this first step, you want to make sure the percentage of the steel reinforcement is good, uh, and after that you calculate A. We'll talk about that in a few minutes. And also after that, check the ductility of the beam to find your value for phi. And then once you have that phi, then you can use that phi to calculate phi mn. So basically, phi times the nominal moment, which is as times fy times d minus a over 2. So, and then you should be able to get the nominal moment. And if that is more than or equal to the ultimate moment that gave you, that you probably trying to check, then your beam is good. Okay, so the ultimate moment here, we're trying to make sure that um, this section can support this ultimate moment. And uh, at this point, yeah, like I said, you've already done these calculations. You've used the dead weight and live load, all the coefficients. You've multiplied all those and done the structural analysis to get this moment. Okay, so let's go ahead and see, calculate our percentage of steel. And all these formulas, they're from the ACI 318 manual. Some people are still using the, like, some probably like from 2000s or 2005. I think mostly like 2010 also, or 11, those range they still use those. But when I graduated, we graduated in 2019, and we used the ACI 318 uh, 19. So it was the 2019 version that I'm using right now. Um, Although some of the values or some of the formulas don't really differ from each other much from the older versions. Uh, so yeah, most of these formulas, or basically probably all these formulas, you can find them in the ACI 318 manual. Um, so that steel percentage is called rho, and that rho is AS, which is the steel area over BD. B is 12, like I say, and D is not H, is this value here. Is from the top of the concrete to the beam to the reinforcement. Okay, so that's basically the extreme fiber of the reinforcement, same as the concrete as well, extreme fiber of the concrete. Okay, so that's that's the value of D. Okay, so just make sure if you can see it's like basically kind of going under, like touching that um under the bars. That's the 24th thing. Okay, all right, so when we do that and put that values in here, we get this. Now on number 9, bar number 9, the area, surface area of the cross section of the number 9 is 1 square inch. Okay, so you want to multiply that by 4. Okay, it's 4 number 9 bars, so 4 times that 1, it will be 4 square inch. That's why I put 4 square inch here. And after calculating that, you get this value. Now your value for this, according to ACI 318, this value cannot be lower than 0.003. Okay, 0.003, that's like, I think is the compressive strain or tensile strain of concrete. I'm not really sure, but anyways, that value cannot be lower than that for flexure. So let me check in my thing here. Yeah, that is a strain on the compressive side of the beam. So that value cannot be lower than 0.003. Okay, so um, so yeah, in our case, it's way more than that. So sometimes you want to check your minimum steel requirement and maximum to make sure you don't uh, under reinforce or over reinforce. So you can find those values and calculate the percentage of the steel as well, minimum steel and maximum steel required. So our case is good here. Now the stress block, dimension A, and that A is this um this here. So first, let's go up here a little bit. So this is your cross section, right? So if this is your cross section, when they did some tests and analysis for like internal forces, find out that the concrete compressive side has this kind of shape, you know, and basically this area here is your compressive stress or strength, and for the steel, the tensile strength is basically, because in the concrete beam, basically the bottom, since the concrete doesn't have that good of a tensile strength, you need the steel. That's why we have the steel in there to like take on those tensile forces, right? So basically anything below the neutral axis in the concrete doesn't really it's kind of like it doesn't do anything really. It's only the steel that holds does the tensile, counter the tensile forces, right? But anything above the neutral axis is taking on those compressive, internal compression, right? So that's why in this representation here, you have the tensile force here only held by the steel. Although the concrete will kind of hold the steel in place and bond with the steel to like make all that happen, but they don't really do any tensile uh, countering. So you get this weird shape here, which you can do that, but like it will take you a while to, I don't know, probably some complicated formula, whatever. So Whitney said, okay, that's why we call this the Whitney's stress block. Like, okay, instead of going through all this pain, let's just turn it into a rectangular maybe, or and she also kind of did her calculations and all that, and found out that, well, this rectangle, this side will be only 85% of the compressive strength of the concrete, right? And then this side is A, which is beta 1 times C. And that C is this value from the neutral axis to the extreme fiber of the concrete, right? So, and this beta 1, if you know C, your beta 1, you can find it from ACI 318 table 22.2.2.4.3. Okay, so you can find the values there. And for in our case, our concrete stress or strength is 4,000 psi, so be only 0.85, right? So I have some yeah. So this table here, right? So for FRMC between 2,500 and 4,000, your beta one is 0.85. Okay, different ones give you different beta values. So in our case we 0.85, but we don't know C. And usually when you're designing a beam, you don't really know C. So sometimes you can calculate it, but like it would probably be easier to not even think about calculating it now. You can calculate A first and then probably determine C later. It's easier that way. So our A is this, right? Our A is this because our compressive, um, how did they find A? It's this. The compressive part of the beam is that area, right? That area times B. Okay, so it will be this 0.85 FRMC times A, right? Times B, which is the width of the beam. It's like yeah. So you get to get you get that uh, you get that area and um, times B, right? And your tensor, you know, in the tension side, it's the um, area of the reinforcement AS times the tensile strength. Right? It's not time the tensile strength, right? Which is the yield strength. Sorry, that's not yield strength. So that's the Fy, right? So this times, I mean this. Oh wait, actually, yeah. So for this to be at equilibrium, this to be it's a better representation here. So for this to be like at equilibrium, this tensile strength has to be equal to the compressive side, right? So we end up having this formula here, C, which is this times B, equals to this. Now, when you uh extract A, solve for A, you get this, and that's how they got this formula here, right? That's how they got A. So usually when you're designing a beam, um, yeah, at this stage you already know AS, which is the steel of the the area of the steel. You know your grade 60,000 psi. You know the width of the beam B. You know the compressive strength of the concrete FRMC. So it's like it's easier to calculate A than calculating C, right? First. So if you use that formula, you get A equals to this, right? Now, when we go in, ductility check, right? Ductility. So in this here, you try to find out if your beam is tension controlled, compression controlled, or in transition. And like the right there, yeah. So we have different uh sections here. So when it's compression control, then your ET, which is the tensile strain of the beam, less than ETY, and that ETY is usually the uh, is the modulus of elasticity of the concrete over. I mean the sorry, not modulus of that ETY is part for the steel, so it's the that Fy yield strength of the steel over the modulus of elasticity of the steel, and that will give you ETY. Okay, So that's how you calculate ETY. Now, and you can find out information in the ACI 318 manual. So if your ET calculated ET here in this case is less than that, then you get a different value of fee. If it's more, if it's between certain number, you get a different value of fee. Okay, so for flexure though, you tension control, then your fee will be 0.9. Okay, so to do this, we have to find beta one. Okay, like I said, beta one is this. Our beta one fall into here, and it's 0.85. Okay, so 0.85. That's why we have it there. C. Now we'll go ahead and calculate C. Okay, so in the example I showed you here, I see if A is equal to beta 1 C, then C equal to A over beta 1, right? So C A over beta 1. And we already calculated A. So to calculate C, we just divide this value by beta 1, which is 0.85, and we get this. Okay. Now we have C. How to calculate ET? Well, ET also equals to this. ET, which is the tensile tension strain, is D minus C over C times 0.003. Okay, and remember I said your D is not your H. D is not the H of the beam, but this value here, distance from the reinforcing bar to the extreme concrete fiber of the beam at the top. So basically that distance there. All right, so our D here is 24, and we already calculated C. C is 692. So when you use that formula here, we get this value 0.004, I mean 007. You can stop there, or just, I like to go a little farther, but yeah. So you use this value now, ET, and come in that same table, which you can find in the ACI 318 manual. This table, wait, not this table, this one here, still in the ACI manual, you'll find it there. And compare the ET to the ETY. Our ETY is 0.00207, I think. Yeah, so our, our ET is 0.007, which is, it doesn't fall into this, it doesn't fall into this, it is in this. So it's tension controlled, and for our, this is like spiral, so you also want to read this. Please read this. It's not here. Well, I guess these two values are the same, but if you fall somewhere here, for example, it will be not the same, or here not the same. So here 0.09, I mean 0.9. So that's how our fee is 0.9. Now that we have that, we're done. All we have to do is plug in this formula, because the Feynman equals to the uh, tension T times the distance between the uh, tension and the I mean the times the distance between the tensions force and the center of the tension force and center of the compressive force. Okay, so this is D minus A over 2, because look, if this is A, this whole block is A, then the middle here will be A over 2, right? A over 2 plus this distance. But um, that distance is what? Or D. So A over 2 minus D, I mean D minus A over 2 will be the distance between the center of the compression and center of the tension, right? So you can use that formula, ASFY D minus A over 2, or um, or that times same thing, so but we use ASFY. That's easier because you have less things in there, or you can also use this. This is another kind of uh, kind of went ahead and instead of putting a, value of a transform with that and row all that still percentage came out with this value, but I rather use this. So when you use that, you find the value, because remember, you also want to make sure all your units are in concordance. Okay, so we have psi, inch. Okay, so everything will be in inch pound, and then after that, we can convert it into foot kick. Okay, because we're trying to measure it against this foot kick ultimate moment. Check to see if our value is more than or equal to that. So to convert it into foot kick, you do 1 inch. I mean, uh, for 1 foot, you get 12 inches. So divide that by 12 inches. And also for 1 kip, you get 1,000 pounds. So divided by 1,000 pound as well, and you get this. And yeah, it's 379. Here we have 350. So it's way above it, which is good. Sometimes if this value is too much above it, then you probably want to adjust the things. Probably you don't want to like over design, because that will cost more money to the client. But you also don't want to under design. So that's kind of a decision you have to make. On your own, but as an engineer. But so I'm gonna put this in my formula here. So if this value is more than what I'm checking against, then right. Okay. uh, Otherwise, right, no good. This is not part of the tutoring, but I forgot to put it in there. So all right, so it will be this, and we should be good. So here it says, yeah, okay, because everything works out. All right, well, thanks for following, and I'll be making another video for how to check for a steel beam as well, like a W shape also. I'll make that as well, and then do some other videos for concrete and like T shape or T beam, design, all that. So if you like this video, please subscribe, like it, and follow me. I mean, subscribe so we can you can get the new videos, updates, and all.